So it appears we have the function generator, we've set out this ammeter here, we've got the resistor, we've got the inductor, and it's being read by the multimeter. So we set the function generator to have 100 hertz coming through, and then we also have set the current at 0.2. Okay, so we've set this to 100, we've set this to 0.2, and now we're going to start reading off these values when we start changing these. We set this to 900, keeping that constant, and we're getting 74. Here we set this to 1000, kept that constant, and now we're only at 82. We're getting to the 1300s, we're keeping that at 2, and we got 105 point something. So this is the last value you got with 2000 and 2 still, and here we got 157.
So this is what the graph of that looked like, and this is our slope that we were to calculate. So when we compare the equation of our graph, y equals, here's the slope, and then there's the f as the function. Here's the EMF, which has the induction constants here, but there's also a little f in there. So we can pull all this stuff out and set it equal to what we have there as the slope, and we're able to calculate their induction, which gave us about a 4.5% error after we looked at the stated value. Quite nice.
So we got a new loop. We got pretty much everything's the same before, but we stuck a smaller loop inside of this thing, and we're gonna read it. So we set this resistor to 2 kilo ohms. We set our current to 2.5, and we set this to 1000 hertz. So with our 2.5 current, we read 17.6 millivolts. With 1000 frequency here and our 2.5 current, we get 17.6 millivolts. And with the frequency at 2000 and the current still at 2.5, we get 31.4 millivolts. The hertz at 3000 and the current at 2.5, we get 40.6 millivolts. We are now going to currently switch these two, and we have set this up the opposite way. So regardless of which one of these that we measured, we got the same readings. As you could see, there's always 2.5, and we had about 17, 31, and 40, which is the same thing we got over there for both of these things.
So according to our calculations, all these numbers were exactly the same, and yeah, we were able to calculate the percent difference, so just proving that the mutual induction is the same for both. In this lab, we're studying inductance, which is going to be a result of the change of flux. So when the flux changes, you're going to get a current that's going to oppose that change of flux. It's going in the other direction. Flux changes can be caused by a change in the area, or the change in the magnetic field, or change in the current. And so you're just going to basically get an opposite current. You could think of it as usually the current would go like from a battery, you'd get the current going in this direction, but the inductor is really more of like acting as if the current is going in this direction, you've got a battery which is countering that current. So that's what an inductor does, actually counters the regular current.